All right. Good afternoon. So, Alicia's going to copy your exam, and the goal is to have it next week. Does that work for you?
And the test.
The test. Exam, test.
Not Friday.
Well, I don't care. Do you want to do it Friday? What do you want to
No.
do? If we have a choice next week, I don't mind that it's offered twice. That's up to you. Do you care?
I prefer just doing all the proctored exams on the same day.
Fair enough.
So Wednesday.
So Monday.
Next.
Wednesday work for everybody?
Next Wednesday, not this Wednesday.
Next Wednesday? Not this Wednesday. Not this Wednesday, correct?
Next Wednesday. October.
October 2nd.
Thank you.
Okay, everybody just sort of pay attention for a second. October 2nd, Wednesday, exam here, normal class period. Right?
Who's going to MSNT?
Anybody?
Okay. Do you want to take it Friday? I have to proctor someone on this Friday. Oh no, you're not going to be here.
Oh, yeah.
When do you leave?
I leave Wednesday. Or Thursday. Thursday morning.
You might want to know.
When do you want to take it? Do you want to take it before you leave or after you leave? Or when you get back?
Do you care?
I don't care.
I'll take it after.
Do I care?
Yeah. All right, Stephen, just let me know when you want to take it.
Right.
Thanks, guys. Thanks, Dr.
Bye. Okay,
Does that mean that more is getting more?
nope, only through today. You have no lecture Wednesday or Friday this week, right? Or Monday, you have 3 days off. We'll make that up later, we'll do it typically late afternoon type of thing, okay? You can come, but I'm not going to be here.
Why aren't you here?
I'm not in town.
Oh, for what?
Okay, so I'm going to MSNT, that's in Portland. I have another meeting on Thursday of this week in Corvallis. I have another meeting after MSNT in Seattle, and one at the end of MSNT in Portland. Do you want my entire itinerary? The hotels that I'm staying at and the people that I'm meeting?
Also,
MSNT is the Throw Science and Technology Conference out there here. Used to be the American Ceramic Society meeting, now we're coupled with ASM and TMS. That will change next year. What's that? My dance card is full. Does that make sense to you? No, probably not. Okay, questions? No, I probably will not think of you during the trip. That was your next question. All right. So, you have homework set 1 was posted to Canvas. Did you see it? Okay, does that take care of it for you? Any questions about homework set? Actually, set 2. Okay. Homework set 3 is almost done. Most of it will be through Excel because most of this is able to be done in Excel. Okay. But anything that's not able to be done in Excel is the plotting of particle size distribution, pretty much, right? Did you do that? Anybody do it? How did it work? I want to share. Pass it down. Great. This is the data here in the upper left, correct? All right. So, this is what you should be looking at. It should look something like this. the top plot, right, would be a normal distribution. The data is clearly not normal, okay? One on the bottom, here's where things become a little bit more interesting. It is mostly log normal, up until you get into the 95 percentile range, and that's not something that is uncommon because of the way that we measure particle size. And that has to do with instrument setup and some other things that sometimes that tail becomes a mess, okay? And it's a very small percentage of the population, so we don't really care about it so much, okay? And you plot it up into 98% basically, and then it starts to deviate. And that's also in the coarse end of the scale, correct? What does that suggest?
You have agglomeration.
Potential for agglomeration. Okay, now I don't know if that's the case, right? But this is also, what would you say? Is that a narrow distribution?
Not with that.
Yes, it is. Okay, and so that probably means that this is a scalped distribution, and so that also comes into this. We talked about that a little bit, right? Conceptually, if we log particle size and then probability axis, cumulative mass finer than, okay, then you might expect initially you have a very narrow distribution, right, a steep slope. If you were to mill that powder, what would happen is your D50 value here, right, will shift to a lower particle size, but also the distribution will get broader with milling. We would expect that distribution to actually eventually develop what we would call a native distribution, where the slopes of these lines become constant with further milling. Okay, so that means that when you mill a powder, when you start crushing a powder or undergo comminution, and you break down that powder, you're going to end up with a distribution, with that distribution, which is more or less indicative of the material that you mill. So that means that different materials will exhibit different distribution types, or different distribution widths as they become milled, as they mill, okay? And then, but you may see that calcium carbonate, for example, has a different slope than sodium carbonate does. That's what we would expect to have happen. What should be done? Well, we should measure a bunch of powders and see if that's how they work out, okay? So industrial processes are set up, they mill the powder, they get a very broad distribution. They're not unhappy with that because they're going to scalp that distribution into portions and sell those portions to different people. Right? And you can always remill a powder. You can always basically scalp the coarse end off and send it back to the mill, and it becomes finer. And you sell that to somebody else. All right? So very little of this goes to waste. Almost all gets used in some fashion or other. These two slopes are supposed to be the same. And you can see that they're not quite. Okay? So you plotted a bunch of data points, that's fine. You didn't need to plot, you need to plot at least, I would say 8 or 10. You got more than you need, but that's all right. That just speeds up the process. Good? Okay. This is what's projected here. This is what you'll see when I post this to Canvas, probably by the end of today. Question 1, question 2, then plotting then number of particles versus particle size. Question 3 is your surface area versus particle size. The x-axis here, because we cover such a broad range, is plotted out as a log scale. And here I intentionally plotted this as a log scale because we've covered such a huge range, from roughly 10 to the 15 to 10 to the 5. So we're 10 orders of magnitude with the number of particles that are in that system from my 0.1 to 100 microns. And in Excel, right, you should know this by now, you can come over here and you can select that to be a log scale, provided you don't have 0 values. Although it's a little bit strange, it seems to plot those anymore. Tells you that it can't, and it does. Not sure how it does that. So this gives you surface area as a function of log of particle size, log of surface area, and scale. So then you're not a surprise. Passes back. Passes back. Okay. So, questions about the homework? tomorrow evening, if you would like, I'm willing to hold a review session. Are you interested? I don't know. What time are you free? You'd rather not? I can take it. I'm free after 4:30. No?
I like five. Five sounds good.
5 o'clock?
5:15.
5:15? Do I hear 6? Why? 5:15? Work?
Well,
Less?
take them all.
Alright. What's it gonna be? Gonna be 5:30? Does that make a difference to you? 5:30. I need some sort of like, indication this is okay.
5:30.
I taught a class in Thailand once actually. It turns out that this means no. Very confusing. Alright, so 5:30 tomorrow in this room. Alright? This is how review sessions work. I will answer your questions. Alright? I'm not going to reteach the class. When you run out of questions, I go home or leave. Good? Okay, so I would recommend that you look at the homeworks in particular, see what's there, and then if you have questions, bring them those. Everybody good? So 5:30 in here tomorrow. Okay, good. Your exam is Wednesday in here, not this Wednesday, next Wednesday. Good? Okay. So this is where we're at. We are really into rheology. We haven't really started this yet, have we? Talked about it yet? Talked about it in my other class. It's very confusing. I can't remember what I teach in which word. Okay, so we're going to start an introduction to rheology. So we started this just a little bit, and okay. So if you take a solid material and you shear it like this, it will deform. And it deforms like this, right? And you get this angle here, which is typically denoted with the gamma sign, okay? And that denotes the strain. So what you have is, you have shear stress, so the amount of stress that's applied to the system, and shear strain, and this slope is the elastic modulus called a shear modulus, right? So you get tau is equal to shear modulus times strain. This is analogous to our stress is equal to elastic modulus times strain for uniaxial tension. Okay? In a fluid, if you shear that material, it cannot maintain a stress in that system. So if you shear, as soon as you shear, the stress that you develop is dissipated by the liquid. So what we do then is that we have to introduce this as a shear rate. So as it shows in the figure here, you have a stationary plate on the bottom, you have a fluid in the middle, and you move the top plate with some velocity in the x direction. And in the y direction, you have a differential velocity based on that distance away from the bottom plate. It is assumed that the bottom plate is stationary, okay? And that the fluid actually in contact with the bottom plate is stationary. That is usually correct. Okay, there are conditions in which that fluid may slip against the bottom plate, okay, and you get a condition called slippage. Shows up in your data. Don't care about that. So this is a general assumption. So what we get is dVx dy is equal to a strain rate, and the dot above indicates strain rate. So what you have is shear stress now versus strain rate, line with a constant slope, and that line is viscosity, and that indicates Newtonian fluid if you have this relationship. Name Newtonian fluid. Did you ever talk about this before here? You have not? Okay. Name a Newtonian fluid. Water. Good. Name another. Say again? Milk, not necessarily. Milk is the suspension of particles.
Oil.
Right? What's that? Oil, alcohol. You have another? Gases, air. Okay? They are all basically Newtonian fluids. Newtonian fluids comprise about 5% of the fluids that you see, roughly. Now you could argue you see water more frequently, but in terms of number of fluids, okay? So what we have is viscosities. Different materials have different viscosities. But a lot of these things, a lot of these materials are not linearly dependent. They do not exhibit this. So what we have here is that shear stress now is equal to viscosity times shear rate. That's our general relationship. Right? And we use this then to measure the viscosity of suspensions. Okay? And that viscosity of the suspension gives us an indication of what's going on with the particles in that suspension for ceramic processing. That's really important for us. I like this chart, most of it. Okay, some of it I don't care for. But if you go to the bottom, here is water. Now, this is in Pascal seconds is our unit of measure. This is 10 to the minus third Pascal seconds. That is a millipascal second. And that's also equivalent to an English unit called centipoise. Poise is named after the French scientist who figured this stuff out initially. And he developed, it's actually called Puiseux flow, about flow through a pipe. Okay? That's what I was told. They don't speak French. So, millipascal second is a centipoise. So 10 to the minus third millipascal seconds, okay, is 1 centipoise. That's the viscosity of water. What I like about this is if I go down one notch here and I look at air, air's viscosity is 10 to the minus 5. So it means it's 0.01 millipascal seconds, or 0.01 centipoise. And what's interesting about that is that we don't think of this as having a viscosity, but it has a viscosity, okay? And you can feel that. You can argue that you feel that with wind or whatever, okay? And that sort of movement of air, right? There's actually a drag associated with that, okay? By comparison, the difference between air and water is the same as the difference between olive oil and water, okay? So olive oil is 2 orders of magnitude higher viscosity than air. Honey is, again, another 2 orders of magnitude. And then I get it to molten polymers. That's where the wheels come off the bus, in my opinion, because there are a huge number of polymers, and I don't know what that means. Group them all together and decide they all have the same viscosity. Bitumen is the high molecular weight end of tar, okay, or tar, high molecular weight end of crude oil. Molten glass at 500 C, 10 to the 12, makes no sense, since you should know by now, or maybe not yet, that I have more or less infinite control over the chemistry of glass, and therefore its viscosity versus temperature curve. So I don't like that one either. How about the one at the top? Glass at room temperature. That's what it's arguing for, 10 to the 40. So glass is a supercooled liquid. Arguably, it has a viscosity. At this point, though, it'd be difficult to tell the difference between it and a solid. Okay? So one of the arguments is that old windows in buildings are typically thicker. They become thicker at the bottom than they are at the top. Why is that?
Because they all kind of more method,
Say again?
forming method of the glass windows.
Okay, so the perception is that the glass slowly flows with time. Nonsense. Okay? That comes under the heading of crap, basically. All right? They put the thick end down when they install the window. Doesn't get any simpler than that. Did you go to the Scholes lecture last year? Did you hear him talk about that? Because he did. All right? Skylights would be somewhat problematic if it's deforming over time, right? They would all eventually invert and collect water, as opposed to just letting it leak. All right, so this is basically viscosity ranges for materials. Gives you an idea, right? The other thing that's important about this, we are talking about orders of magnitude difference in viscosity, not linear. Okay? Water isn't twice as viscous as oil, bicycle oil. It's 100 times less or 10 times less viscous. So this log scale thing is important to us. When we look at shear rates for typical processes, we see some similar differences in magnitude of the shear rate. High-speed coating, 10 to the 5 to 10 to 6. That's 100,000 to a million reciprocal seconds. So that is the unit essentially on this. This unit is time inverse time, s to the minus 1. Reciprocal seconds says it at the top, okay? Certain things such as lubrication and gasoline engines, up to 10 to the 7th, that's 10 million reciprocal seconds. Spraying and brushing, 1,000 to 10,000. Mixing and stirring is 10 to 1,000. Depends on how rigorously you stir. All right. Chewing and swallowing is entertaining at 10 to 100 reciprocal seconds. Draining under gravity, 0.1 to 1. Excuse me, 0.1 to 10. And then surface tension level. You get an idea that there are huge differences in shear rate depending on the process that's being involved. Now, it turns out that if our fluids are Newtonian, then the viscosity is constant. So if I go to really high shear rates or really low shear rates, I have the same viscosity. But most of the materials that we work with do not have a constant viscosity, and their viscosity then changes with shear rate. So most of the suspensions that we deal with are considered to be shear rate thinning. Now, what that means as I increase shear rate, the viscosity appears to decrease. Now the problem is this. If I look at shear rate versus shear stress, I have this nice Newtonian behavior here. But in real systems, they might behave something more like this. Okay? And down at the bottom here, if I were to extrapolate this back, I would get what's called yield stress. Okay? And if I were to look at this yield stress value, it says that I'm offset. In other words, I'm going to start to shear my material, and at low shear rates, the viscosity appears to be very, very high. And at high shear rates, that viscosity appears to decrease with increasing shear rate. So what I get here is that if I measure this behavior, I'll draw it schematically here. I get shear rate and I get shear stress, and I get a data point. So I measure shear rate at a given shear stress, I get a data point. Okay? And I can draw a line through that data point. I can say that I follow my relationship of tau equals viscosity times shear rate. So viscosity is equal to shear stress versus over shear rate, excuse me. Okay? So what I'm doing is I'm making an approximation that says that this is on a line, it goes through 0, and there's my viscosity. Okay? So the way that viscometers work typically is that we fix the shear rate value and we measure drag on our spindle or on our device that tells us what the viscosity is of that material. So the point is, how much stress or how much force do I need to put in divided by my cross-sectional area do I have to put in to maintain that rate? So if I have a highly viscous material, I have to put in a greater amount of force to keep that spindle turning at the same rate. Okay? And I can measure then how much force is involved. If I go up to a higher shear rate, okay, and then I have another shear rate viscosity pair, I might have now an A to 2, and it has a different slope. So A to 2, this is shear rate thinning, because A to 2 is less than A to 1. And I can keep doing that. If I do enough of these, I end up with a curve. These values are called apparent viscosity. They are what I measure. Okay? And this seems like an odd statement. Viscometers do not know what has happened before. I am collecting data sets, right? I'm collecting a set of data which includes a shear rate and a shear stress value, and I get from that a viscosity value. I am measuring discrete points. The viscometer is unaware of what happened in the previous point and is unaware of what happens in the next point. It's only collecting the data, and it gives me that data in a set of discrete points. Now, what happens then is that my viscosity appears to decrease with increasing shear rate. That is shear rate thinning. Okay. Now, this says pseudoplastic with a yield stress. This is actually probably a more accurate description of what the actual data sets look like. Okay? And what I have here is a series of lines, basically, that have different viscosities as I collect my data sets. If I look down here in this region right here, I actually have this, right, that then eventually starts to curve over. Shear stress, shear rate. Notice in this region, what do I have? Oh wait, I have a constant viscosity. My viscosity any place along this line is the same. Understand? So this region in this curve here is Newtonian. When I get above a certain, either you can look at it as a certain critical shear rate or a critical shear stress, above that point, my material becomes non-Newtonian. It exhibits shear rate thinning. So at very low shear rates, I get Newtonian behavior. As I go above a certain shear rate, I start to see shear rate thinning dependence, meaning my viscosity decreases with increasing shear rate. And I get a curve that's like this. So if I were to plot them, eta 1, eta 2, eta 3, and I keep going eta 4, eta 5, eta 6, and I start plotting this data, plots like this, almost exactly like shown there. Log shear rate, log viscosity, or log, excuse me, not shear stress, log viscosity. Its apparent viscosity, I get a curve that looks like this. Okay, so this is my Newtonian region. Okay, where I'm eta sub 0 is then Newtonian-like. So if you were to plot this in general, and you say, well, log viscosity versus log shear rate, Newtonian fluid has a constant viscosity, independent of shear rate. Okay, that's what water does. That's what a lot of oils do. Okay, that their viscosity is independent of shear rate. Well, I have that region here. This is now viscosity that is a function of shear rate. We might denote that with a gamma dot subscript afterwards, although we don't usually use that connotation anymore. And then over here, eventually, I get now what's called an eta infinity, or an infinite shear rate region where my viscosity is again Newtonian. Now, what you could do is you could argue that in this case, if I go out far enough, my difference in slope between my viscosity values becomes very small. So if I were to think of it sort of this way and do my shear rate on the x-axis, shear stress on the y, it comes up like this and then keeps going. And eventually when you get out here, these all have the same viscosity at very high shear rates. That's the argument. This is that curve. This is artificial. It's not real data. It's a calculated curve based on the equation in the upper left, okay, upper right, excuse me, and that's called the Kuru-Yasuda relationship. It's not particularly important to us, except that we have these three regions, okay. Now, this is really important. We plot log of viscosity, not linear viscosity, and we plot log of shear rate, not linear shear rate, okay. The reason is that we can learn something from this curve. If I plot that on a linear scale, it would look like this. And if you get that, what's your conclusion? Oh, it's a shear rate thinning. And then you get a poor grade. Okay? So if you take this and you plot it that way, that's what. Okay? Because you are talking about orders of magnitude differences in shear rate and orders of magnitude differences in slope. okay? And when you plot those, you will get this curve in the middle. That's what we want. Turns out that we can end up with a number of things. One thing we like to do is say gamma dot equals 1, and we're going to then have our viscosity at gamma dot equals 1. Why do I do that? Because I can fit an equation to this line. Here's my shear rate thinning behavior, log viscosity, log shear rate. And at 1.0, okay, I have a viscosity value, and the log of 1 is, what's the log of 1? Yeah. So it is the intercept of an equation that describes that line. Good? I don't care whether it's my viscosity goes through that point or not, right? You then have a way to look at this viscosity, and then you get a shear thinning exponent. How sensitive is that change in viscosity to change in shear rate? It turns out that I can have an infinite number of materials that have the same viscosity at 1, but different shear rate behaviors. In fact, one of my students did a senior thesis several years ago and looked at a whole bunch of viscosity data that we generated and looked at the dependence of that slope on degree of dispersion, flocculation, and coagulation in suspensions. Nice work. Okay, we'll talk about that perhaps when I get back. All right, so this is our general curve for viscosity, and this describes most of the materials that we see. There is one more thing that happens, is this. If I plot this data, it comes down like this, and it will shoot back up again. This is log viscosity versus log shear rate. At this point right here, we call gamma dot critical. That is my critical shear rate. And above that shear rate, my system becomes dilated. What does that mean? That means that as I shear, my viscosity increases. Okay? So what happens then in the particle suspension, it's a really nice article on this by a guy named Hoffman that I will try to dig out for you. Did these really elegant experiments that demonstrate what demonstrates what's happening in these suspensions. So as you're shearing, the viscosity decreases. Why does the viscosity decrease with increasing shear rate? So we are restricting our discussion to particle suspensions. Good? We can talk about polymers if you wish, and they behave somewhat similarly. If I talk about particle suspensions, right? Why does my viscosity decrease with increasing shear rate?
You get planes of particles that flow over each other.
Okay, we get layers of particles. So we start off with a random structure of particles, and we start shearing that structure. What will happen in shearing is that the particles will start to align in that shear field. And the more they become aligned, and I pretty much did the stuff, jumped a whole bunch of steps here. The more they align, the lower my drag in the system, the reduction in viscosity. So I end up with layers or lamella in here that allow the particles to align. And as I'm shearing that material, as I get more alignment of those particles, not necessarily orientation, just particles one following the next, okay? And they'll form these layers. As long as my shear rate is sufficiently low that the layers are maintained, then my viscosity continues to decrease with increasing shear rate. But if I shear too fast, particles then are unable to stay in their lane, and they get kicked out, and when they get kicked out, the system locks up and expands, and your viscosity increases, and that's called dilatancy, and you get it above a certain critical shear rate. Okay? We've been interested in this phenomena for a long period of time because it turns out in ceramic forming systems that this Newtonian region, A sub infinity, is basically our plastic forming region for plastic forming ceramics. Okay? But if I go too fast, the system locks up, and you see that as a defect that's generated in forming processes of tearing, typically. The system can't handle it, and it will tear. This was data actually that we generated for alumina, okay? And here's your shear rate thinning regime. viscosity decreases, well disperses here in the closed circles, comes up and then it goes back up. And then if I add salt, I can manipulate that around a little bit. And the idea originally was that we were looking at the potential to use suspensions as armor, energy absorbing systems, because when you shear, then it absorbs that energy and locks up. I feel that was a great idea, except that this shear rate that you have here in this rate region is actually the shear rate where you move. So you would lock up as you move, which would be entertaining. Okay? And also the other thing is that projectiles are significantly higher shear rates than that, 10 to the 5, 10 to the 6 reciprocal seconds. So we weren't quite in the right range, but we could manipulate that behavior. The best example of dilatancy is at the beach. So you have the beach, water, fishies are out here, okay? This is dry up here. In this region right here, the sand is saturated with water, okay? And if you step on the sand, right, it discolors around your foot, that's a representation of the shoe, okay? And so when you step on that, you get a discoloration region around your shoe, okay? Why? Because you've exceeded this critical shear rate. What you have here is particles. There are two conditions that are necessary, okay? High solids loading, okay? So for dilatants, high solids means a minimum amount of water. This is 60 volume percent. That's above my limit, okay, for particles in suspension. High solids, the second thing is, it needs to be dispersed, okay? That means the particles are acting independently. If that's the case, when you shear this system, which we actually do vertically, we're going to do it this way. When you shear the system, this particle wants to move that way. This particle has to move out of the way in order for that to happen. Then the system then dilates or expands to allow those particles to rearrange. That expansion then locks up the system. And what happens is that all these particles are this liquid, it's filled with liquid, but when you expand, that liquid gets pulled back in as you try to expand that network. That causes a discoloration. So what you're seeing actually is when you step on it, that top layer of sand is depleted of water because the system's trying to expand, water gets pulled in, capillary action takes over and locks all the particles up. But if you stand there and wait, okay, so when you step, you're out here, right? And when you just stand there and go back to here, and it gives time for the particles to rearrange, and what happens? You will slowly sink into the sand, right? Okay? Now, it's not dramatic like, you know, Indiana Jones and the quicksand thing. It's not that, right? You sink in, but if you are in a hurry, you try to remove your shoe, you remove your foot quickly, you'll often leave your shoe behind because it's the same thing on the way in as it is on the way out, right? Dilatancy when you step on the sand and dilatancy when you try to go the other direction. Okay, so you can see this. So the best place, right, if you want to run is right on the edge because that's then basically hard when you step on it. Very difficult to run up here if nobody wants to run in the water. So, okay, the general picture, right? This is dilatancy, and we see that in ceramic processing systems. So, with that in mind, go back to here, okay? We have 5 basic properties or behaviors of suspensions and fluids in general, okay? But suspensions in particular we're interested in because they apply to ceramic processing. First, you have Newtonian. Now, there are 2 categories. Rate dependence, okay? So we're either rate thinning or rate thickening. So dilatancy is rate thickening, okay? So Newtonian is independent of rate and independent of time. Now, we can debate that, right? Everything has a characteristic time. Characteristic time has to do with how fast your process is based on how fast the particles can rearrange, okay? So, and it's called a Deborah number. It was invented by a guy named Reimer. And a Deborah number if you've been to my office, there's a one-page article on the Deborah number that's hanging outside my office for the last 4 or 5 years, 3 years, something like that. The reason was that a commencement speaker came, it was a guy, I'm gonna say it was the guy who invented the polychromic glasses. But Deborah and I came up one day, and the idea is that in the Bible, Deborah talks about the mountains move before the Lord type of thing, that his frame of reference or God's frame of reference versus our frame of reference is very different. And so therefore, events that occur within the time frame for particles to rearrange have a low Deborah number, and a high Deborah number means you exceed that rate. So my point here is that water is a Newtonian fluid. Fair enough? Okay. Anyone here ever done a belly flop? How many people done a belly flop?
Not very well, but yeah.
How can you not do a belly flop well? Never mind. So, so the issue is, right, you hit the water, it's like it's a solid. So you are actually moving faster than the water can react. Okay, probably because of area. Okay. Fall out of an airplane though, problematic. All right, because you hit the water and you will end up trying to move the water faster than it can be moved, and it's like hitting concrete. Not good. All right. So there are time dependencies, but that time frame is so short with water that we typically ignore it. Same is true for particle suspensions. Pseudoplastic is also called a Bingham fluid. It is rate thinning, but it is time independent. Okay? Time independent means that as I shear that material, I do not see a change in viscosity. Now, you have to subtract or get out of the idea that, well, when I change my shear rate conditions, it takes a few moments, maybe half a minute for the system to get to steady state. Thixotropic materials, these are in pseudoplastic materials, equiax particles, no time dependence to speak of. When I go to thixotropic materials, the next category is shear rate thinning, but it also is thinning with time. So what I have then is, instead of having nice spherical particles or even irregularly shaped particles that have no aspect ratio, if I get plate-like materials, okay, like this, they will align in that shear field, okay, and what will happen is that my particles, which are random, as I shear it, they will become aligned. And you'll notice here that I drew the particles in the middle unaligned. That was intentional, all right? So what happened is that as I go from t equals 0 to t equals 1, and then I continue on to t2, now what would happen is that you would see that more of these particles are aligned, so that this thickness of this aligned region is getting thicker with time. Okay, so the longer that I shear that material, the more aligned it gets, and the reduction in viscosity that I see associated with that alignment shows up as thixotropic behavior.
Will that also affect your particle packing based on how they're aligning themselves?
It appears to, so that if you shear the system, your packing typically gets better. So, thixotropic behavior is observed, not typically, if this is alumina, we don't see it with alumina, typically, that no thixotropic behavior. If we get to clay, though, traditional ceramics, now the platelets are hexagonal platelets, okay, like this, and those platelets will align in that shear field, and you'll see then that you end up with a severe or serious difference in viscosity. So if you come into the lab or the studio, and you have a bucket of suspension sitting there, you can take a spatula, if it's been sitting there for, let's say you mixed it up yesterday, okay? You come in today, set the spatula, and the spatula stands up. Mix it up with the spatula, viscosity drops dramatically, and then it may take several days for it to get back up to that viscosity that you saw when you first walked in. Okay? So what happens is these particles align. When you take the shear field off, Brownian motion starts to rearrange the particles from being aligned like this, eventually to be back to be randomly oriented in that suspension. That takes time for that to happen. So that is thixotropic behavior. Very not commonly observed in particles with equiax nature, such as alumina or silicon carbide or whatever, but commonly observed in systems with the shape. Dilating, we mentioned, is rate thickening. Above a critical shear rate, viscosity shoots up. Okay, and above that critical shear rate, then The system essentially locks, that's dilatancy. And our last example is rheopectic. Okay? That is thickening with time. It is analogous to thixotropic behavior, but it's rate thickening. What do you think must be the conditions for rheopectic material? What were the conditions for thixotropic?
Aspect ratio.
One has an aspect ratio, and then there are two other things, right? Highly loaded and dispersed. So you expect for rheopectic the same sort of thing. Highly loaded, dispersed, but with an aspect ratio that causes this, or have some sort of shape that causes the system to lock up as you shear it. Some alignment that creates a region that's unable to flow. Don't have an example of a rheopectic material. You could say, well, if I make cement paste for sidewalks, I mix it, and with time it thickens. That's true, but I consider that to be irreversible. Right? Setting reactions are not reversible. All of these others are reversible. I take the shear off, suspension reverts back to what it was before. Okay? So these are our 5 rheological behaviors. I'm going to ignore this for the moment. We'll come back to how we measure later. There are 5 factors that control suspension rheology. Okay? And yes, I'm really stuck on this. Okay? And the reason is simple. These factors are not independent of one another, for the most part. And because they're not independent of each other, when you start looking at the rheology or the flow behavior of particle suspensions, what you find is that since these factors are interacting, it can become very difficult to decipher what controls the flow behavior of suspensions. This I consider to be a mechanism by which we can do that. So these are an order of importance, and you must know them. Well, it's going to be on the exam. It'll be on the exam next Wednesday or Friday, whatever day it is we're taking the exam. You're taking the exam. Okay? 5 factors that control suspension rheology in decreasing order of importance. So the number 1 for small particles is particle-particle interactions. That's most important because I can take a suspension and I can change the way the particles interact, and I can change the viscosity of that suspension by several orders of magnitude with a small change in pH or a small change in, or the addition of a dispersant. Okay? Particle concentration. If I increase the concentration of particles, the viscosity goes up. That's by far the most abused, if you will. Suspension is too viscous. Okay? High viscosity. Viscosity is resistance to flow. High viscosity, I add water, I dilute the system, viscosity decreases. Not good for me in terms of ceramic processing because ceramic processing requires you to remove that water and to build up a wall thickness or make a plastic body. So it costs me money to add water into the system because then I have to remove it. Okay? The third is particle size and distribution. Broader particle size, better packing, less drag. Okay? If I have smaller particles, more particles, hence the homework question, right? How many particles based on size? And you can see that I have orders of magnitude more particles as my size gets smaller. Therefore, I have more drag in the system. So as the particle size gets smaller, I get more drag in the system. If I broaden the distribution, big particles and small particles fit in between the large particles, an apparent reduction in concentration, and therefore a reduction in viscosity. Particle shape is number 4. If I have plate-like particles, they have a higher drag in the system than spheres. So as my particles deviate from spherical, my viscosity increases. Okay? Very difficult to quantify. And last is rheology of the suspension medium. When I first did this, there were 4 factors that control suspension rheology. And then I got invited to give a talk at an injection molding conference. Turns out viscosity medium is important to them, so I added a 5th one. We don't worry about it so much. Okay? These are the 5 factors that control suspension rheology. Write them down, memorize them, because you're going to see them again. It's a simple question. It's going to show up. It says, list the 5 factors that control suspension rheology. That's pretty much exactly what it will say. In order of decreasing importance. Oh, this is the list. You know, years ago I used to flip that in order of increasing importance. Nah, it's too much trouble. We're doing this. Got it? Questions? Okay. Tomorrow, 5:30 here. bring questions, you run out of questions, I leave. Good? Okay, enjoy your evening.